Warm greetings everyone. Welcome to our assignment presentation where we discuss about our scheduler program for our arcade game. My group consists of Cameron, Tram and myself, Tamid Zaman. First, let me give you an insight of the assignment. We were asked to make a scheduler program for our arcade game in a shopping mall where the scheduler program would run through a waiting queue and select customers, and there is also a priority fact at play where members are given more priority compared to non-members. For our presentation, we look into the choice of our algorithm, priority handling, solution to the starvation problem, and value tuning. For our choice of algorithm, we had three algorithms: first come first serve, shortest job first, and round robin. First come first serve and shortest job first are easier to implement and have less context switches. Context switches is the time overhead taken to switch from one customer data to another customer data, and in comparison, round robin gives equal time to every customer. For the cons, first come first serve and shortest job first has longer wait time and can lead to starvation, whereas round robin has more number of context switches. And we went with round robin. For priority handling, we had two options: priority scheduling with round robin, where lower wait time is given to higher priority compared to giving more runtime or CPU time for the higher priority. And we choose the latter one. We still might face into some starvation issues, thus we look into aging, where dynamically priority is handled for lower priority so they don't go into starvation, and we reduce the discrepancy in runtime between high and low priority so they are closer. For aging, we had two options. In the first one, the priority is reduced every time the customer goes through the queue or the task runs through the CPU cycle, compared to the next one where after a certain number of CPU cycles or the customer going through the queue, they are allowed to run to completion.
To increase the performance of the scheduler, we've looked into time quantum, high priority task time quantum multiplier, and number of CPU turns before running to completion. Time quantum. So for time quantum and multiplier, we've considered how smaller time quantum leads to more context switches. However, larger multiplier leads to fewer context switches at a cost of larger longest wait time. And we done a simulation where we test the data in order to turn these two values. It was found that the shorter than baseline time quantum 4 times unit paired with a multiplier of 2.25 get the best overall results. For the number of CPU turns before running to completion, in our test simulation, we've tested values from 1 to 8 and found the best value to be 5. So this is our code. Some key points to notice is that the time quantum is actually the time allowance, which is 4. And then we have the multiplier is 2.25 and the CPU turn is the attempts, which is 5. So for the next part, we'll show a quick example how code works. Just keep in mind that when a queue isn't empty, high priority user max time allowance is 9 based on our time quantum and multiplier. And low priority user max time allowance is 4. After that, if they switch out 5 times, they can play until completion. So here we have a high priority user 0 at time 0. Since there isn't a queue, user 0 can play as long as they desire, which is 22 time slot. Then at time 10, a low priority user arrives. Now the queue isn't empty. Thus, user 0 can only play for 9 time slot before switching with user 1. And then after 9 time slot, at time 19, both users will switch out with each other. User 0 is put back into queue with 3 remaining time slot on the machine, and need to wait for 4 time slot for user 1, which is at time 23, before switching again to play their remaining time of 3, then leave. Now user 1 is back into the queue with 9 time slot left on the machine. They either wait for the user 0 to complete their remaining time or max of 9 time slot. But in this case, user 0 completed in 3 time slot, then leave, and that is at time 26. And that is all. Thank you so much. We hope the explanation on our code design was clear and enjoyable for you.